Good day everyone, and my name is Toong, and I will be presenting on a review on recent wheel-rail interface friction management. So I'm from UTHM, University Tun Hussein on Malaysia, from the Faculty of Mechanical and Manufacturing Engineering. Right, so this is my presentation outline. First, I will be presenting on the introduction of friction management, and then to the subtopic of dry and wet wheel rail contacts, and also sanding. And after that, I'll present on the conclusion, which I will conclude the research gap that I have discovered from this review. Right, first of all, introduction to the friction management. The wheel rail contact is a complex and imperfect link due to the small area and loaded with highly concentrated stresses. So the conical wheel shape makes the wheel set a mechanical amplifier limited by the transverse plate with partially sliding surfaces. From this figure, as we can see that the contact patch is made up of two regions. One is the stick region and also the micro slip region. So you can see that the traction distribution and the region of the slip. So when the attractive force is greater than adhesive weight, the saturation value of the tractive force is reached and resulting in the contact patch dominated by slip. The contact is then considered as pure sliding. Traction is influenced greatly by the climatic conditions, especially under wet condition induced by rain and snowfall, which causes the loss of adhesion, and it may cause the slip and damage to both the wheel and rail. In tropical countries, wetness and humidity is capable of reducing the coefficient of traction to a value lower than the allowable minimum coefficient of traction, which is 0.2. 0.2 is the limit, the minimum allowable coefficient of traction. So in countries with 4 seasons, they don't only have wetness, but they also have snowfall and also dried leaves, autumn leaves, which cause the leaf coating on the rail and which causes adhesion loss. Poor adhesion is a serious matter because it will cause high frequency screeching noises, severe rolling contact fatigue, exacerbate the rail corrugation, poor braking, and also poor taking off of the train because of friction. And if the friction is too high at corners, it is at curved tracks, it is also able to cause wheel climb and derailment of the train from the rail. Next, I'll be presenting on dry and wet wheel rail contacts. So from this figure, you can see that there are several lines which indicated by different conditions. One is by dry condition, wet condition, and also lubricated dry condition. As you can see, lubrication can instantly reduce the coefficient of traction effectively. And as you look at the green lines, you can see that once the application of friction modifier is done, the coefficient of traction from 0.5 reduced instantly to 0.1. The unstable pattern of the graph of the line is due to the distribution process of the lubrication applied. From this figure, you can see that the wear in dry condition is mainly by plowing, while in wet condition, delaminations and flakings can be seen, which is the figure in B. The reason of this is because of hydropressure when the fluid is trapped in the initial cracks. So as fluid enters the cracks on rail initiated by shear and pressed by the rolling contact of the wheel, the contact pressure is transmitted hydraulically via the crack to the subsurface of the rail. The fluid is then entrapped and pressurized inside the crack, which then results in the generation of squeezed film pressure. Rough surface has high asperity, which could provide a better grip than smooth surface. Therefore, greater surface roughness gives higher maximum coefficient of traction to a wheel-rail contact. This is confirmed by the recent work of Chen, both theoretical and experimental analysis, where under wet conditions the coefficient of traction reduces as the surface roughness decreases regardless of the contact pressure. However, based on the theoretical analysis, which employed a numerical method that adopted the hydrodynamic lubrication (EHL) theory and Greenwood-Williamson's stochastic model, different trends of coefficient of traction can be obtained by varying the surface roughness as shown in this figure. From this figure, we can see that the axial load will actually cause very little influence on the coefficient of traction, as Wang has reported that with 17 tons, 31 tons and 25 tons, and the trend are similar with the increasing of slip percentage, but the trend, the deviation from the three different axial loads are actually the same. In order to simulate curved rails, the angle of attack is implemented. So as we can see that 0 degree, which represents tangent rails, while 0.2 degree, 0.3 and 0.4 degree represents curved rails. Wheel-rail contact in smaller radius curve will cause the decrease in coefficient of traction even more. This is because the longitudinal creep force of the contact area would reduce by decreasing the curve radius, which leads to the loss of adhesion. The next subtopic is on sanding. Sanding is mainly used to remove and also to improve the adhesion in leaf coated rails, or maybe in grease or when during climbing. So this is the figure of the sanding mechanism, and also the sandbox on the buggy of on the ballast wagon. So sanding actually restores adhesion, remove leaf layers, and also lubricates the contact at the same time while restoring electrical conductivity, because as the leaf layers are removed, the wheel and rail are able to contact again and also to conduct electricity. So what causes sand to be able to have such characteristics is because the mechanical interlocking mechanism, which causes the wheel and rail to be able to have the interlocking effect because of the sand. From this image, we can see that the dry baseline, which is clean rail, and also rails covered with leaf layers, the blue line and the green lines respectively. And there are two types of sanding, which is initial sanding and continuous sanding. In initial sanding, where the sand is injected into the interface during the starting of the experiment, we can see that the coefficient of traction will rise and reach an initial peak. After that initial peak, the coefficient of traction reduces and then increase again. So it will increase until it meets the coefficient of traction of the dry baseline. This is most probably because the sand layer has been completely removed, so the interface is clean. While for continuous sanding, which the sand is continuously injected into the interface, we can see that from this pink line, where the coefficient of traction is maintained at 0.3, the sudden drop in coefficient of traction of the dark blue line is because of the breaking of compact crushed sand layer on the wheel-rail interface. From this figure, we are able to observe the residue of the leaf layers, which is on the left, and also the powder of broken leaf layers on the right. This is the effect of initial sanding. Whereas in initial sanding, the first part of when the slip is low, the leaf will will be removed slowly, which we can observe in the left, while on the right is when the slip is high, the leaf layers will turn into powder, which can be easily removed even by finger, just rubbing on it, and the powder will be removed. Arias Cuvas have conducted extended studies on particle size. So as we can see that there are 3 different sizes which is studied by Arias Cuvas. So in initial sanding, he realized that M sand is the best, while in continuous sanding, L sand is the best. When Arias Cuvas conducted the experiment, the test on electrical insulation, he found out that S sand and M sand will cause total insulation and an open circuit on the rail. This is because the interface is filled up with crushed compact sand. From this image, we are able to observe that the size of the particles is able to cause surface deformation and strain hardening. The surface deformation in S sand is minor and almost unnoticeable, but for L sand, both wheel and rail specimens, we are able to see the deformation, subsurface deformation, is high, and a highly strained layer is formed, which eventually causes strain hardening. Slip will also causes the increase in coefficient of traction, but at the same time it will cause surface deformation as well, including cracks on the rail surface. So from this image, we are able to see that 1% slip has a minor deformation, while 10% slip has severe deformation for both wheel and rail. In terms of feed rate, when the sand feed rate increases, the coefficient of traction reduces. This is because more sand particles has entered into the interface and caused a sliding effect. Finally, in the conclusion, we've realized that as a conclusion, from this extensive study, I've concluded that there are 3 gaps that are available for future study. The first is a satisfactory method to enhance adhesion and avoid severe wear. At the same time, is still uncertain. Even though sanding is good, but it will still cause high wear rate on the rail and also on the wheel, while lubricating with lubrications will have hydropressure issues, which causes delamination and also flackings on the rail. The influence of the second gap is the influence of different types and different compositions of sand is not studied and also unclear. Its effect on this coefficient of traction is unclear, because mostly they are using railway sand. In most of the studies, they are using railway sand or they are using silica sand. So perhaps different type of sand or different compositions of sand can be used, since different sands exhibits different hardness level and may interact differently in the contact interface. Finally, leaves are actually good lubricants. So because it is able to reduce the coefficient of traction to a low level, it is also can be used as a solid lubricant to prevent hydropressure issues. Perhaps the black leaf substance that I've mentioned earlier can be used as solid lubricants. So that's all for me. Thank you.